So look at the paper in 2008 going through question 27. Okay, so in question 27 we're told a very large bird watcher of height 2 meters and 100 kilograms mass sees a nest in a tree. And when he is 18 meters from the tree, his line of sight is 45 degrees to the horizontal. And we're asked, if the egg falls from the tree, how long will it take to fall? Okay, so we need to find out how high this nest is from the floor. So let's start by drawing a diagram. So if we draw our tree here with our nest at the top, when he is standing here, bear in mind he's 2 meters tall, when he's 18 meters from the tree, his line of sight makes an angle of 45 degrees to the horizontal. And we can label this as x. So that's the height the nest is above his line of sight. So we see we have a right angled triangle and we have the opposite side and the adjacent side. So we know tan of 45 degrees will be the opposite side over the adjacent side. And therefore x is 18 times tan 45. And tan 45 is 1, so x is 18 meters. So we see it's going to actually fall 20 meters, x plus 2. It has the fall to his line of sight, and then the extra 2 meters to the floor. So how do we find the time? Well, we clearly use SUVAT. So we know s is ut plus half at squared. So s is ut plus 1/2 at squared. Well, let's write down what we know. So we know its displacement s is going to be, we'll take downwards to be positive, so 20 meters. It starts with an initial velocity of 0, so it's falling from rest. V, well, we're not concerned with that for the time being. A is gravity, 10, and t we want to know. So summing that in, we get ut is 0, plus half times 10 is 5t squared. Therefore, 20 is 5t squared, or 4 equals t squared, and therefore t is 2 seconds. It takes 2 seconds to reach the floor. Well, how fast will it be travelling at the bottom? Well, there's two ways you can do this. One is from energy changes and one is from SUVAT. We'll do SUVAT because we started with that. So we know that v squared is u squared plus 2as. Well, that's 0 squared, 0 plus 2 times 8, 10 times 20, so 200. And therefore v is equal to, 2 times 20, so 400. Therefore, v is equal to the square root of 400, or 20 meters per second. Okay, so part C says the egg strikes the ground and stops after 1 millimeter. If its mass is 20 grams, calculate the force required. Okay, so how am I doing this? Well, we know that it strikes the ground with a speed of 20 meters per second, and so it has kinetic energy. So it's going to stop, so it has to lose this kinetic energy. So it has a change in kinetic energy. And where's this energy going to go to? Well, that's going to be equal to the work done by the force. So that'll be equal to force times the distance. So its change in kinetic energy, well, it strikes with half times its mass, 20 grams, 0.02 kilograms, times its velocity squared. And it strikes with 20 meters per second, so 20 squared. And that's equal to F times the distance, 1 millimeter, 0.001 meters. Okay, so F is therefore equal to 0.01 times 20 squared over 0.001. That's equal to 10 times 20 squared, which is equal to 4 kilonewtons. So that's the force required. And part D, to calculate the work done by this force and compare it to the gravitational potential energy of the egg. Well, work done is simply force times distance. So that's 4 kilonewtons times 1 millimeter. So that's 4 times 10 to the 3 times 1 times 10 to the minus 3, which is 4 joules. Now, what was the gravitational potential energy of the egg? Well, that's mgh. So that's its mass times g times the height it was at, which is 20 meters, and that's 4 joules. So you see, that's actually equal to the work done. So the work done by the force is equal to the gravitational potential energy it had at the top. Okay, so part E says, to stop eggs from smashing, the birdwatcher places 10 centimeters of foam around the tree. if this foam compresses to half of its thickness when it's struck by an egg, how much force will be required and how long will it take to stop an egg falling, to stop an egg from breaking? Okay, so let's work out. So we know it strikes with the same speed. It's a normal egg just striking. So we know it's going to have a change in kinetic energy equal to half times the mass times the speed squared. And that's going to be equal to the force that acts times the distance over which it acts. Well, we know it compresses to half of its thickness. And it was 10 centimeters thick, so it's going to compress by 0.05 meters, 5 centimeters. Therefore, F is equal to half times 0.01 times 400 over 0.05, which is 80 newtons. Okay, well, how are we going to find the time? So we have a speed before, we have a force, and we know that force times time is equal to the impulse. So force times time is equal to impulse, which is mv minus mu. Well, v is 0, because we know it stops. So the ft is equal to minus mass 0.02 times u, 20. Therefore, coming up here, force is equal, time is equal to minus 20 times 0.02 divided by the force. And remember, the force is actually negative because it's acting against the motion. So that's minus 20 times 0.02 times minus 80. And that comes out as 1 over 200 or 5 milliseconds. Okay, F, calculate the minimum energy required to return the bird to the tree. Well, this is the presumption that he travels completely vertically up the tree. He starts at the base. If we just quickly sketch our tree. So if this is our tree, we have our man down here, and he must travel, we're presuming if it's the minimum energy, he's only going to expend gravitational potential energy. So he'll move vertically upwards. So you must overcome the force of gravity, the gravitational potential energy, to reach that height. So that means that the minimum energy is equal to the mass, well, that's now his mass, plus the mass of the egg, times g times the height, that's 20. He must move up 20 meters from the bottom to the top. And that's equal to 2 times 10 to the 4 joules, or 20 kilojoules. Okay, so the last part of the question says, the birdwatcher decides to boil the egg. And we're asked to calculate the minimum required efficiency of a heater used to boil the egg if he wants to use no more energy than was required to return the egg to the tree. So we know that he required 2.0 times 10 to the 4 joules to return the egg to the tree. So how much energy is required to heat up the egg to get to the boiling point? Well, we know Q is mc delta T. The mass of the egg is 0.02 kilograms. We're told to assume that the specific heat capacity is 4 times 10 to the 3. And that the change in temperature, well, we're told it starts at 20 degrees and we're told it has the same boiling point as water. So that's 100 degrees boiling point minus 20 at the start. That's how much energy will be required to heat the egg. Now, so we're told that he wants to expend no more energy than he would have used to put the egg back in the tree. So that means he's going to put in 2.0 times 10 to the 4 joules of energy into boiling water. That's how much he's willing to give up. Now, the efficiency is the amount of that goes into boiling the egg. So if we call the efficiency E, that means 2.0 times to the 4 times E, the efficiency, is the amount that goes into boiling the egg. And we need this to be at least equal to the amount of energy that's actually required to heat the egg, which is this energy here. So now we simply solve for E. So dividing across, we get that the efficiency E is equal to 0.02 times 4 times 10 to the 3 times 80 divided by 2 times 10 to the 4, which comes out as an efficiency of 32%.